Section 21.5, the force on a current in a magnetic field. So if we imagine a wire that's hanging in between two magnets, because it just has to be a wire that has some current passing through it. Turns out that wire is going to feel a force from the magnetic field if you line it up just so. Why is that though? Well, if we picture this wire, which is just, it's set up to some sort of battery here, a DC source, right? And the wire comes around, comes down, goes back around to the negative side. That's going to set up a current, the current flowing from the positive side down to the negative side. And the current here is, we can imagine these positive charges that are moving in the same direction, right, along the wire. If we have positive charges moving through a magnetic field, there's going to be a magnetic force. We can once again use our right-hand rule, and we're going to line up our thumbs in the direction that the charges are moving, the current, line up our index finger in the direction of the magnetic field, and then that shows the force, which is coming off to the side. And that's enough that it can make the wire actually move, right? It could swing up, as in this case, so that it is at a higher point. Or if you have a strong enough magnet and current, the wire can actually jump out of there because the force is so abrupt. How can we say this mathematically? How can we describe how the current carrying wire also experiences a magnetic force? To do that, we're going to look back at our equation of the force that a charge feels from a magnetic field. So this is one of our key equations of the chapter. So the charge times the speed of the charge times the magnetic field times sine of the angle between them. But we remember velocity could be written as distance over time. And so we can start thinking about time here. And what we're going to do is multiply this by 1, by delta t divided by delta t. You can always multiply by 1 and it won't change any numbers. But the lower one we'll put below the delta q, and then we'll keep the one on top next to the v. Why is this useful? Well, delta q over delta t, that's our definition of current. So that's just I. And the speed that the charges are moving at times the time interval over which they're moving, that's going to tell us the length through which they're moving, L. That in this picture is shown by this wire. It's a wire of length L. So this is how we can arrive at our equation of the force on a current. So the magnetic force that acts on a current carrying wire is given by the magnitude of the current times the length of the wire that's in the magnetic field times the magnetic field times sine of the angle between the wire and the magnetic field, right? So we have the current and the wire are pointing this way, the magnetic field is pointing to the right, and theta is the angle between them. So for this example, we can again use our right-hand rule. It's just instead of using our thumb as velocity, our thumb is going to be current. It's the same rule though. So we line up our thumb with the current, our index finger with the magnetic field, and our middle finger or our palm will then give us the force, which is up in this case. Let's look at this in an example. So the force and acceleration in a loudspeaker. The voice coil of a speaker has a diameter of 0.025 meters, contains 55 turns of wire, and is placed in a 0.10 Tesla magnetic field. The current in the voice coil is 2 amps. Determine the magnetic force that acts on the coil and the cone. B, the voice coil and the cone have a combined mass of 0.02 kilograms. Find their acceleration. So in A, we're solving for force. In B, we're solving for acceleration. How do you think we're going to solve for acceleration? Probably using F equals ma? I think so. That's a good approach here. So as we take a look at this, what other information is given to us to help us solve for the force? Well, we know the amount of current, 2.0 amps, so that's our I. We also know 0.1 Tesla, that's the magnetic field. So that all is good. What else do we need? Our force is equal to I L B times sine of theta. So as we think about that equation, we know the current, we know the magnetic field. What about the length and the angle? So for the length and the angle, we need to think about what is the effective length of the wire within the magnetic field. So the wire within the magnetic field is all of the wire that's wrapped around this coil. How long is that? Well, that's where the other numbers here help us out. They mentioned that there's 55 turns and that there's this diameter of 0.025 meters. So if we can figure out how much distance it is to make one turnaround, then we can multiply that by 55 to get the total length of the wire. We can imagine unraveling it to measure. The way we can get that length of one turnaround is just going to be the distance around a circle, or the circumference, which you may know as 2 pi r. In this case, they gave us the diameter, so we can multiply it. We can divide it by 2 and then multiply it by 2, but we could also note that it's the same thing as pi times the diameter. And then if we want to get the length of all of the turns, then it'll need to be 55 times that. I'll just do for all of this. All of this times 55 will give us the length. So that is an important little detail there. The other thing we need to figure out is the angle between the length and the magnetic field. So notice here in the cross-sectional picture, you see the wires that have current either coming out at us with the dots or going into it, but the magnetic field is passing right perpendicular to those wires. So because the magnetic field is going perpendicular to the wires, it's going to be an angle of 90 degrees, which simplifies things. And you could incidentally also show that the direction of the force, both for the top and the bottom half, will give you a force that is going out. So that's a useful practice of the right-hand rule. Okay, I think we now have a framework for how we can approach this of solving for the force. So let's try putting it all together. So we have force is equal to current times length times magnetic field times sine of theta. We have the current is 2 amps. The length is 55 turns times the circumference of one turn, pi times the diameter, times the magnetic field times sine of 90 degrees. So this comes out to 0.86 newtons. Units still work out to newtons. The acceleration, as we suspected, is from Newton's second law with the force divided by the mass, and it's an acceleration of 43 meters per second squared. That is pretty hopping. That's quick. So your little speaker is putting out quite a bit of acceleration to be able to bump the tunes that you hear. So you should appreciate that.